Good afternoon. My name is George Paris. I hope we're recording. Yes, we are. And I would like to introduce to directed energy materials. Ooh, that was traumatic. Basically, my name is George Paris. I mentioned that earlier, and I'm an organic chemist. I'm also the CEO of the company Directed Energy Materials. Directed energy materials was formed with the idea of using various types of energy to cause chemical transformations to make novel materials. We believe that our inventions will find many applications in manufacturing and medicine. Back in the period 2010-2020, we got interested in this area for a variety of reasons. If you go back to that time frame, there were two areas that were very exciting. One was in the materials area, carbon nanotubes and graphene, and the other one was in the manufacturing area. This would be additive manufacturing with 3D printing. That was some of the very early, very exciting times in 3D printing. 3D printing was going from being a prototyping tool into an actual manufacturing tool. You're looking at materials like carbon nanotubes, graphene sheets, buckyballs, things like that. And you've had this great technology, this 3D printing technology, where you could make these very intricate patterns that you couldn't make any other way. And the idea is, hey, we're going to make some really novel uh, structures. We're talking about the structures for like a space elevator. We're going to take advantage of the great strength of carbon nanotubes, etc. We're going to make suspension bridges with incredibly long cables and whatnot. And we're going to make all sorts of very intricate designs in between. And so, how do I fit into this as an organic chemist? Well, it turns out when I got to looking at the technology that was being used to make these carbon compounds, uh, I found that methane is the material that the people are using to make carbon nanotubes. It's like that's not what an organic chemist would start thinking about. And became apparent to me that hey, maybe there's a much better way to try to do this. Maybe we don't have to have 10,000 degree temperature and all this other stuff and the limitations which the thermal the decomposition of methane requires to make carbon nanotubes. And so I started looking at the literature a bit and came up with the idea that um, there's a chemical compound, 1,1-dichloroethene. If you happen to be a chemical engineer, you probably call it 1,1-dichloroethylene, or you might call it vanillidine dichloride, VDC, or dichlorovanillidine. That's another possibility. Anyway, the formal appropriate chemical name would be 1,1-dichloroethene. There are two chlorines on one carbon, two hydrogens on the other, and double bond between the carbons. It's very much like uh, uh, ethylene, ethene, which is just if you didn't have chlorines, you just have ethene. And anyway, this thing forms a polymer very readily. And Dow Chemical Company was doing this research, and they discovered, hey, you can make this polymer very easily, and what they call poly vinyl dichlorovanillidine, and PVDC, I guess is the name they called it. And the polymer has interesting properties in that it resists the penetration of oxygen. So the idea is we'll make fibers or we'll make uh, uh, film, and we'll use that to create an oxygen barrier, which is very good if you're like wrapping up your sandwich. You want a sandwich that's wrapped up in this stuff, and oxygen can't get to it, and the sandwich will stay fresh for a long time. Or you can put it over a bowl of salad, and oxygen doesn't get to the salad and retains its capabilities. And so these things were pointing it towards being a household use item. Uh, but a problem developed in that it was turned out that if you heated it up to 125 to 200 degrees Celsius, you lost all the HCl. You lost at least 1 mole of HCl. For every mole of the monomer you put in, there's every molecule of the monomer you put in, you got 1 mole, molecule of HCl out. And you end up with a polymer. And the real problem here is that this temperature range you could reach with a microwave or with an oven, and so your typical housewife was likely going to cause problems with this. And so the product was dropped, not pursued, because of the problems with its instability. Now, it turns out if you continue heating this, you can drive all the HCl out. Unfortunately, I am in the middle of this and you can't see the end of that. This may be a problem throughout the video. But in any event, there's this, you can, at 700 degrees C, you have driven all HCl out and just have carbon left. Now, on the one hand, that sounds very good. The problem is that this is not a useful form of carbon. It's just an amorphous mixture of materials. And the point that I have here is that, I'm a chemist. We think about how to solve these problems. And we think we can fix this. And we have some ideas along the way that we're going to talk about. All right. So going back to this time frame, as I said, 2010 to 2020, you had this what's called a hype period, hype of interest in graphene and carbon nanotubes and whatnot. And a lot of people got interested, not just us. There's a number of patents that got issued and companies got formed at this time frame. And I found a company, Directed Energy Materials, based on a patent application. Actually, the provisional patent application went in 2017, and the title was something like Methods and Materials for Creating Patterns of Carbon and Other Elements on Substrates or Within Liquid or Frozen Media by Directed Energy Deposition of Carbon and Other Elements. And I was going to use the approach that the chemical reactivity that I just discussed here. I knew I could produce carbon. I think I can also produce carbon in forms that are useful. So keep this in mind. Now, it turns out that the Patent and Trademark Office does not respond on the whim of applications, and we had to argue our way through, and we ended up with 2 patents, one having to do with the deposition of carbon and one having to do with the deposition of metals. And so that's the 2 patent applications that the actual patents were issued in 2024 and 2025. So it took quite a while for that to happen for us. But our predicates go back to 2017. Okay, now in the meantime, lots of stuff was happening over the last 10 years, and especially in the area of microelectronics, integrated circuits and whatnot. You probably have all heard about Moore's Law, and you've heard that Moore's Law is reaching some sort of crisis. Moore's Law basically says every couple of years we can double the number of transistors on a particular a chip or a volume or space. And so if you keep doing that, you come to a point where the transistors are getting down to atomic size. And when you get, you go down from meters to millimeters to micrometers to nanometers, well, chemists are working on angstrom levels. That's another order of magnitude below nanometer. So a nanometer is about 10 angstroms, which is about 10 times as big as an atom. So when you get down to the nanometer scale, you're talking about something that's about 10 atoms big, and there are lots of chemical compounds that are that size. And so we're starting to get out of the engineering materials business, and we're getting into chemistry business. So here we're making these multi-layer materials, and I am blocking up this thing here, but basically we're out of the realm of materials and we're into the realm of chemistry. All right. Now, this video, or this actually, the URL that is here on on my left, it's my left, your right, is the uh, in red. This is done by a company called Branch Education, and with the support of ASML, the manufacturer, and it's a very good video. You're really going to watch it. I recommend it strongly. Go on, it's on YouTube. Look it up, watch it, and you'll educate yourself regarding how integrated circuits are manufactured. Basically, the machine which is being hidden by my cameo here is the machine that's used to do this. It's used something called EUV, that's extreme UV light. You have to have very short wavelengths in order to do this work at the scale that these people are working at. And the EUV light is focused in many exotic ways and used to do what's called photolithography. Now, every step of this, every time you want to make another layer of this product, you basically create photolithography. The steps in photolithography are multiple. First, a uniform layer of material is deposited on the substrate. A masking polymer is applied and exposed to radiation. The unwanted portions of the mask is removed. The deposit layer is modified, and then the remaining mask is removed. And then you do it again. Okay, and you build this layer up, this structure up layer by layer, using every time you go to a new layer, you're doing another cycle of photolithography. So this is a very repetitive process, goes round and round and round, and takes up a lot of time and a lot of materials. And every time you go through one of these steps, you run the risk of destroying everything you've created before. So the point I would make is that maybe photolithography is not always the way, there's probably places where you have to have lithography, but what can you do without lithography? Directed energy with deposition is another approach. And our patent, starting in 2017, methods for forming mechanical and electrical components by deposition of graphitic carbon and/or metals on substrates in selected patterns determined by the application of directed electromagnetic radiation without lithography. The patents include the deposition of metal oxide insulators. And those are the two patent numbers. You can go look them up on YouTube, not YouTube, look them up on the internet and see what the Patent and Trademark Office has given us. When I say electromagnetic radiation, what am I talking about in particular? Well, there's three major approaches here. One is you could use a moving point of incidence of a laser beam, for example. You could take two laser beams and have an interference pattern created by these two laser beams. Or you could create a collimated beam of light, and you could have a pattern built into that collimated beam. And any of these approaches you could use to create patterns on the surface. None of them involve photolithography. We're not putting down a polymer, etching the polymer away, da 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 da. We're going directly from the light to the deposit on the metal, on the substrate. Now, I would point out that there's a company called Fraunhofer that had similar idea. They have come up with they've patented a machine. They've built and patented a machine which allows you to create these interference patterns with laser beams. It's an optical device which creates this interference pattern. And they're using it to do something they call direct laser interference patterning, DLIP. Now, when they say patterning, what they mean here is they're etching the surface. They're not depositing anything on the surface. That would actually be in conflict with our patent, but they are etching the surface. They're taking surface materials away. Very interesting idea. and they find certain interesting behavior of the surface just because it's been etched and has these patterns on it. And on the left, you see some of the theoretical approaches. If you have 2 beams, 3 beams, 4 beams, etc., you can get different patterns. And you can, if you want to put enough beams in there, you can get any pattern you want to. They're looking at relatively simple, relatively regular beams here. But their approach again is in the removal of material. They're etching away the surface, leaving behind material, whereas we are talking about depositing material on the surface. Interestingly enough, I believe that the same hardware that they have invented and patented could be used uh, with our approach to deposit materials on the surface, and so they're not incompatible ideas. All right, so what I've talked about so far is stuff that we have done in the past. This is all pretty much covered in our patents, but that date back to 2017, I guess 2018, that time frame. The point that I like to make here is that we sat on this and we did not fully develop this because we wanted to see what we could get out of the Patent and Trademark Office. We finally got that last year, year before last, and this has created within us motivation to continue down this pathway. And what we have done primarily in the 2025-2026 timeframe is submit a number of new patent applications. And what I'm going to talk about here today is these new patent applications. The the bold white lettering here are the what we call our internal key names for these things. The actual names that the Patent and Trademark Office would recognize are the official names that are in red. So when I say interstitial composites, everybody here knows what I'm talking about. But Patent and Trademark Office might only recognize methods for forming interstitial carbon and metal network composites. So keep that in mind. When we talk about the interstitial composites, this is actually an area that's pretty well developed. There's a lot of work in fiber reinforced plastics and things like that that overlaps in the area we're working here. Our idea is we want to, there's all kinds of fibers. You got fiberglass, you got carbon fibers, you have asbestos, you have rayon, you have nylon, you have cotton, wool, etc. All kinds of fibers. And our idea is we want to permeate those fibers with our monomer, in particular the 1,1-dichloroethene, polymerize it, creating an orthogonal fibrous material. Our fibers would be orthogonal to the base fiber. And then we can convert that into carbon by heating it up. And that might be a very interesting type of material. As I said, this is a very busy area. There's lots of patents in the area. There's lots of claims in the area. And we have a very small sliver of claims in this area. Unlike our previous patents are very broad, and we've covered a lot of area with it. But in this case, we have a very narrow application, very narrow patent claims here. But it is there. All right. Now, the problem that I stated up front is that when you have this polymer of 1,1-dichloroethylene or 1,1-dichloroethene, when you have this polymer, you can go the first step, works very well, lose 1 mole of hydrochloric acid. The problems with trying to control that all seem to happen after that stage. And so most of our thought process lately has been, how do we solve that problem? We think we can fix it. Can we fix it? We don't know. There are 2 major approaches. One is directed self-assembly, and one is modification of the reaction mechanisms. Directed self-assembly basically takes the idea, if we're doing this reaction in a confined space, if you're in solution or if you're in the gas phase, the molecules can all move around and do whatever they want to do and come together in any pattern they want to come together in. But if you're in a confined space, so the molecule can't actually move, and can't get out of the space and can't go in all different directions, then it's going to be forced to do certain things. This is directed self-assembly. And so we think we could use directed self-assembly to work on this problem. And the other thing is we think that we can modify the reaction mechanisms. We think we understand the reaction problems, the reason the mechanisms go the way they go, and we think we can fix that fairly straightforwardly as well. And what we do is we make something called a carbon nanotube machine. That's uh, probably a provocative title, but it's it is descriptive of what we're thinking about here. Remember, I'm an organic chemist. We think like organic chemists. The organic chemists wanted to make a fiber like rayon. We would extrude that fiber through a spinneret, and out would come a fiber which we could then bundle up and use as a fiber. Well, the idea here is on a micro scale. Now we're looking at a fiber which is going to be on the scale of a carbon nanotube, which is many, many, many times more finer than a rayon fiber, for example. What we're going to do here, we're going to take a barrier of some sort that separates our cold side, our high pressure side, and our low pressure side, or hot side, and we're going to put our monomer, this magic compound, 1,1-dichloroethene, on the cold side, and we're going to force it through this very tiny hole. The hole is going to be on the scale of a nanometer to maybe 10 nanometers. This is roughly like a zeolite. Part of the idea came from what we call molecular sieves. Chemists were aware of molecular sieves that would absorb some compounds but not other compounds. And so, if you think about a zeolite, some compounds will go in and others won't. And so the idea is these monomers will go in there, but polymers won't. And so as the monomer goes in, it tends to form a polymer. And then the polymer, it tends to be decomposed. But because it's constrained, it's not going to do all the things that the unconstrained polymers will do. And we think that by constraining it to a very limited number of options here, that we have a much better chance of getting a carbon nanotube out than in just heating up the polymer by itself. So this is if this works well, it would be pretty remarkable and might open up the door quite a wide way. I might mention I take some encouragement from the fact that I've noticed that when people are making carbon nanotubes from an iron catalyst, the smaller the iron catalyst particle, the better the carbon nanotubes. Because basically, I think the iron particles, if they're on the same scale as this 1 to 10 nanometers, then you have a much better chance of getting a single nanotube coming off of there, which is, I think, what we're trying to strive for here. All right. So we could even envision like a piece of metal embedded in this barrier, and just let the monomer come in one side and the carbon go out the other side. More of a conventional approach. In any event, let's move ahead. Obviously, if we think we've solved the problem for carbon nanotubes, we ought to be able to do something for monolayer graphene as well. So here we go. There are many claims to making graphene, by the way. Anybody with some electrical heating tool can make it can make graphene. Uh, People are taking waste paper and waste plastic and heating it up, flash pyrolysis, and doing all kinds of stuff, and saying we've got graphene. That's okay, great, wonderful, have a great day. Uh, in order for graphene to become useful as a building material for complex tools, you need to be able to grow monolayer graphene in the size and shape and place desired, and preferably at low temperature, because you can't just heat everything in the world up to 5,000 degrees and assume that sort of everything's going to work out well. All right. So the way most people have done this in the past, the primary process is the chemical vapor deposition. You could also call it carbon vapor deposition. Basically, they're taking organic compounds, heating them up to the decomposition point in the gas phase, and what happens is most of the stuff goes off as a hydrocarbon or hydrogen gas, and then the carbon fragments fall out onto the surface, and that's where they accumulate. That's where you make your graphene or your nanotubes. But this is still a high temperature process. It turns out that if you go back, I went back as far as I could find, there was actually a patent from 2017. This lady, Geraldine Bott, Ohio University, uh, she patented a process which looks very much like the current process that MIT is talking about. It's you're depositing using chemical vapor deposition. You're depositing carbon onto uh, a copper surface. Now, what this fellow John Hart had to say over at MIT points out, hey, we're going to need lots of this stuff if that's what we're headed, if that's the way we're going to do this. And so they are striving towards like mass production of it. And but here again, it has it's a very specific form. It's not just general application materials. And he says you're going to need to make acres of it. Okay, this is a monolayer graphene. Obviously, an acre of monolayer graphene would not be a very big mass of material. Actually, it's one atom thick, two-dimensional. I'm not quite sure how much that would weigh, but it would not be a lot of mass. All right. There's a company called Paragraph Limited. Paragraph, this is their own quote from their own material. It says, Paragraph is the first company in the world to mass produce graphene-based electronic devices using standard semiconductor processes. And they have some patents going back to 2019, 2022. And if you read their patent application descriptions here, you find that what they're doing is they're doing chemical vapor deposition onto a spinning disc. So they're using spin coating or spin coating technology and chemical vapor deposition simultaneously to decompose some organic molecules. Among them would be methylene dibromide, by the way, and depositing the carbon onto the surface. So this is as close to someone doing what we're talking about as I've seen. Here again, this is actually a chemical vapor deposition technology, and they seem to be successfully coating the surface with a uniform monolayer of graphene, which is useful. Now, can we make graphene without chemical vapor deposition? Remember, I'm a chemist. That's what I've always wanted to do. When a chemist looks at graphene, he sees a couple of polymers zipping together with 2+4 cycloaddition reaction. So when I started thinking about this, I'm thinking like, why won't this work immediately? It's like I've got these polymers with these alternating double single bonds, and why doesn't this just automatically happen? And the 2+4 cycloaddition reaction is showed in this inset here. It's called a Diels-Alder reaction. Uh, the guys who formalize this work. But the question is, it doesn't. It should go beautifully if you're quick thinking organic chemist, but something screws it up. And the question is, why doesn't it work? And so my thought in analyzing the work that has been done was to go back and look at what was happening and say, okay, why did that happen instead of what I would think would happen? And so using that as an intro, after reviewing the various published studies, and there are a number of published studies in both manufacturing and in scientific literature, of the pyrolysis of PVDC, we came to the conclusion that the subsequent 2+4 cycloaddition of this polymer. Once you have you lost 1 mole of HCl, you've got this polymer which has alternating double single bonds. And for reasons that were not clear in any of the authors writing, it didn't happen at ambient temperature, which is kind of interesting because 2+4 cycloadditions frequently happen at ambient temperature. You usually don't have to heat them up. But for some reason, you had to heat this up to 175 degrees. And we think that the reason you have to heat it up is because the polymer itself is rigid and doesn't allow the chemical reaction to occur because it's in a rigid polymer. And so once you heat the polymer up and melt the polymer at 175 to 200 degrees Celsius, then this reaction can occur. The 2+4 cycloaddition can occur. But at this temperature, when you get up to 175 degrees, you've got the 2+4 cycloaddition creates allylic halogen positions, which I've marked in this the graphic here. And basically, they can undergo homolysis. In other words, they undergo just the carbon halogen bond breaks. And when that happens, it gives you free radicals. It gives you chlorine radicals. It gives you carbon radicals. And this is where the random interchain connection starts. And so you end up getting random cross-linking. And you can also get, I'm obscuring trichlorobenzene is one of the byproducts that comes out of these things when you heat it up this way. And so the idea is, how do we prevent this from occurring? And the idea is, okay, we're going to try to fluidize these polymers by using a solvent. And so our strategy is to use a solvent to help mobilize the polymer chains at lower temperature that will facilitate the Diels-Alder reaction without forcing homolysis. We still have to get rid of the HCl. And the way we're going to do that is not by having a homolysis, not by having a free radical reaction. We're going to use a base, potassium t-butoxide, to pull off the protons and kick out the halides, such that this is a reaction that is not going to go by a free radical mechanism. And so we believe that by keeping the whole reaction temperature below 175 degrees, that we can cause the polymer to go to a graphenic approach as opposed to this random gamish of free radical combinations. Those are the hydrogens that would be plucked off by the base. All right, once you've got graphene and carbon nanotubes, questions comes up, well, what do you do with that? I mean, what can that be used for? And the answer is, well, let's try to make some electronic devices. And research and manufacturers are starting to consider new materials and paradigms to make transistors. I mean, after all, we have this big crisis with Moore's law going on. And so graphene is frequently mentioned in this context, and it's immediately discarded because it, quote, has no band gap. Now, I'm a chemist. That's not terminology I normally would use. Basically, what is a band gap and what's a transistor and why is this problem that needs to be solved? Well, basically, a transistor is just a switch. You turn it on, you turn it off. You use a electrical potential to control the flow of electrons through a semiconductor, okay? And why does it need a band gap? Well, the band gap goes back to the fact that in all recent transistor development, this is the traditional silicon-based transistor manufacture. They use materials in which there's what they call a field effect, causes the blockage, causes the stoppage of electronic flow, the so-called field effect transistor. And the most recent configuration is what they call a gate all-around field effect transistor. Now, the electrons move freely across a graphene sheet, and thus there's no obvious way for a traditional FET type transistor to work. Okay. So I know that by all the electrical engineers look at this will say, well, what are you going to do? You can't, if you don't have a FET type transistor. Well, we're in chemistry now. We're not in materials anymore. We're talking. You're talking to a chemist, not to a material scientist. And so I'm sitting here and I'm thinking, how does a chemist create a band gap with a strip of graphene? It requires some change which can reversibly affect the mobility of the pi electrons in graphene. I've got it, okay? No problem. Here's what I'm going to do. Complexes of aromatic compounds with transition metals, especially chromium, are very well known. This is dibenzene chromium. You'll notice the scale here, those are angstroms, so we're talking about 2 or 3 angstrom size. A whole bunch of different structures. There's no reason we couldn't do this with a extended sheet of material. This one at the bottom here, those are carbonyl groups. You can use chromium hexacarbonyl as one of the starting materials. Do all sorts of exotic things. A variety of chemicals have been made and characterized. And you may say, well, tell us about the band gap. Well, here comes the band gap. Basically, the so-called mobile gap, that is a conduction band, is the E2U and E2G levels of the aromatic group. And what happens is the electrons from those fall into the localized orbitals around the chromium, and that stabilizes this complex. And this is actually pretty stable. In fact, a lot of transition metals will do very similar things. Ferrocene is an example. It's probably a very well-known compound. And you've got so you take your conductance band, and now you've turned it into a band gap. You have something which will stop the flow of electrons through the conduction band. We have a band gap by, however we created it, we have a band gap. Fisher and co-workers did a lot of this original work back in the 1950s. And the idea is here you have an electric signal, changes the electrolytic structure of chromium, and that opens up the channel for your transitional work. It turns out there's been work, I can't pronounce this gentleman's name, Decos G something or other. He showed that this is a reversible oxidation reduction process, and it's very fast. And so I think that we're talking about processes that do make sense. Once you have, if you can make a transistor, then you can start making much more exciting devices. And so we have a patent application in which we describe how you could use that material to make these devices. And this is an example of what we have drawn out here. We obviously have a number of graphics in our patent application. Now, by the way, this summarizes the entire part of the uh, directed energy materials. You may say, though, what were you doing between 2018 and 2025? And it turns out because we were sort of held up on what we thought was our initial goal of making materials using directed energy, materials that would be particularly useful in electronics and other areas. We sort of branched out and took paths of least resistance and did work with other things, including proton beams and some converging laser technology and whatnot. And we have a number of, I guess we have 4 or 5 issued patents, and we have several patents pending in this area. So the message to all of you out there is that we are a intellectual property company, and we would love to have people come along and say, hey, we'd like to work with you, or we'd like to use your technology, we'd like to license your patents. We'd like to invest in your company. So if you're out there and you have any of those ideas, please get in touch with me. Uh, there are two other videos of this type from last year, near before last, in which I had my personal phone number and my email address. My email address for informational purposes is antimony, ANTIMONY _121 at hotmail.com. And you can email me. You can find me on the internet. I'm all over the internet. George E. Paris, Parris, and live in Gaithersburg. I graduated from Georgia Tech and NC State University, and I've got a lot of stuff that's available in there. You could track me down if you want to find me. So we would be very interested in hearing from you, and we would be willing to entertain almost any sort of offers or discussions. And that is our status as of August 1st, 2026. Thank you for your time.